Hello, I'm Zach Patterson, and I will be presenting our work, SugarC, Scalable Desugaring of Real-World Preprocessor Usage into Pure C. This work was done along with Zeno Zhang and Brent Pappas, alongside Dr. Wei and Dr. Gazillo. So, let's look at this code, where we have a variable x, and it's being assigned 256, and then printed it out. Depending on the preprocessor if-defs, uint or char, x is either going to be an unsigned int or a character. And when this is compiled, what we can see is that if we have uint defined, then we have x as unsigned int x and x equals 256. And what's being compiled if char is defined is char x, and then x equals 256. This, however, might be a bug, as the character limit is 255, so we may be introducing an issue that we don't know about, and we can't detect this unless we actually compile the code under the condition char. So this is something very common in software product lines, which heavily make use of the C preprocessor in order to support different machines and language features or tool features. So most static analysis is variability oblivious, meaning it can only run on one configuration at a time and it can't check for any others. If a configuration has two values and there are n configurations, then we have 2 to the n unique configurations, which is completely infeasible to actually test, despite the fact that there are only going to be minor differences between the different versions of the code. This is why variability-aware analysis is much more attractive. So, in order to run variability-aware analysis, we have two real options. We can either try and recreate the already existing variability-oblivious analyses for new preprocessor-aware data structures and representation, which leads to the currently existing, ever-widening gap between the current state-of-the-art in variability-oblivious analysis and what's capable in variability-aware tools. Our other option is to adapt the representation of C and its preprocessor into a format that's more easily translatable to existing oblivious tools. If we wanted to rewrite an analysis to be variability aware, we would need some kind of representation. Typically, this is currently done through the variability aware AST, which is currently produced by both SugarC and TypeChef as existing tools. However, if we have an AST analysis, it would require a non-trivial number of updates in order to actually work on this. And this is because this new variability-aware AST will have new preprocessor nodes along with new data structures to represent how the preprocessor affects the code. On the other hand, if we convert our representation into a pure C code output, or desugar it, this is a style that we can try and easily adapt an existing tool that's variability oblivious to work on this. A couple tools have tried to do this in the past, specifically Hercules and C Reconfigurator, which are built on top of TypeChef and SugarC respectively. However, these are both informal approaches, which means they don't run on any formal grammar, and therefore it leads to a limited support of actual C constructs. Even more so, Hercules is built off of TypeChef, which has the assumption that there are no type errors, which limits the configuration space you can explore. SugarC, on the other hand, has its transformation rules applied on the formal C grammar. And so, as for the contributions of SugarC, we used the design of syntax-directed translation on the official formal C grammar in order to make the support for what C constructs we have very explicit, which leads to the implementation being a bit more sound than past work. We also include some novel optimizations to work with real-world code, and we introduce a new micro benchmark, DesugarBench, which uses configuration options in order to explore different language features. To evaluate SugarC, we do feature support comparisons with both Hercules and C Reconfigurator, and we try and run SugarC on real-world code to show scalability. So let's talk about desugaring. We consider the preprocessor to be syntactic sugar. So to desugar it is to remove the preprocessor while maintaining semantic equivalence. In other words, we want to take the compile time variability that exists and translate it into execution time variability. So if you can see, going back to our example from before, we've got unsigned int x, which in our desugared output is represented as x1, and char x represented as x2. So we duplicate the possible definitions and then rename the output. This leads to a few issues. So for one, if uint and char are both defined, then x is multiply defined, and in printf, when we reference x, we now have a type error, because this is an illegal configuration when referencing x. Similarly, if uint nor char are defined, then x has not been defined either, and so to use it in printf is another type error. In the valid cases of just uint or just char, we wrap the access to x1 in a configuration space related if statement based off of what is associated with the variable. So when we go here then to char, we can see when referencing x2, we wrap it in not uint and just char. So SugarC is built on top of SuperC, which it uses as a variability-aware parser, and then we operate through syntax-directed translation. And what this means is that we have some kind of grammar made up of production rules, and at the end of each production rule, once we complete it, we perform a semantic action, which means it's going to take some piece of information from all of the tokens that were used in the production rule and associate them with the new token we create with the production rule. And as we said, our grammar that we use is the formal C grammar. So the tokens are all associated with a multiverse. And so this is something based off of past work. What it really is a mapping of a presence condition or a configuration space and some kind of object or value. Our multiverse, however, enforces two important invariants. One being that all conditions are mutually exclusive, and two, the union of all conditions is going to be logically true. And so what this means is regardless of what presence condition I put into a multiverse, I will get some value out of it. So as we can see here in this example of the multiverse representation, all of the code associated with uint and not char is associated with x1. Everything that's char and not uint is associated with x2. And in the other covering cases, we have a type error. So our semantic actions are written in Java as our tool is implemented using Bison to parse. And so what you can see in our transformation rules, or the semantic actions, is that we take the Cartesian product of the data associated with each token in the production. Each token is going to be associated with a multiverse, and so the Cartesian product is performed using a scalar operation. And the presence condition of the product of this operation is going to be the logical and of the presence conditions. So going back to our example of the two different x's, and x being assigned 256, we look at the production for the assignment statement where we have ID equals symbol expression. And what we see is that when we reference x, the ID, the multiverse associated with this is going to be x1 with uint, x2 with just char, and if it's both of them or neither of them, we have an error. The equal symbol is going to be represented with logically true, as there's no configuration options associated with the equal symbol here. Now, when we take the Cartesian product, we are going to be using the scalar concatenate or append string options. So x1 and x2 now have an equal sign at the end of them, and we don't append anything to an error because it is an error. The presence condition is going to be the and of the two, which is just going to be, since we are anding with true, it is going to be itself, or identity. So uint with x1, char with x2, and for both or neither, error. We then take this multiverse and do the Cartesian product of this alongside expression, which is just 256 and logically true, because there are no presence conditions associated with the expression. And so, as you can see, when we take our Cartesian product, and so therefore the multiverse associated with the assignment statement token we're producing, x1 is 256 or x2 is 256, depending on just uint or just char, and in other words, we have an error. And so, like we said, we handle errors. And the reason we're able to do this is because we do type checking alongside parsing simultaneously, which allows us to easily implement static type errors in our code. This allows us to look at a much larger configuration space without the need of the entire space being valid. This is important as past work has relied on the assumption that there are no errors, limiting the configurable space that you can explore. We also use SugarC's forking and merging in order to check for parse errors, which we also implement alongside the real code and initialization function at the top. This allows us to parse configuration spaces which might not even be legal to parse in some configurations. So SugarC in practice. Structs grow very rapidly in real-world code, and if we were to just take the Cartesian product of every single field and just create a new struct for all possible combinations, we end up with 2 to the n structs for the n configuration options that may appear in the structs, which is obviously exponential. And real-world code typically makes very heavy use of type defs and structs within inside of structs, which means that the output is going to grow extremely rapidly. And so instead, we take the Cartesian products that we've made and we append them to a list of products and then put them all together. So in our output, what we choose to do is to duplicate and add all the fields. As you can see, we've got our 2 type defs for this size, and we use this size on f. And then when we use f in our desugared output, we can see that we have both definitions for this size 1 or this size 2. Then later, when f is referenced, what we choose to do is to wrap the access in the presence condition of word size being 32. Now, let's talk about structs and size of. So, in our code, we've got x and y as 2 structs, where x has 3 fields and y has 2, being int, or int short. And then later we initialize an array using the size of differences. So what we do is the exact same thing as before. We duplicate the fields in struct y that could exist based off of condition A, and just put all of them into one struct. However, now, the size of y is going to be larger than the size of x, which would be a negative sized array and is therefore an error. So what we choose to do is to recreate a size of stand-in struct for a and b respectively, and then use the size of those instead. So here we have just the 2 ints, and then in this case we have the int short. And so you might be asking, if we have to explode and recreate every possible struct configuration anyways, what's the point of putting them all together? And that's because not every struct is going to be used in size of. And so in order to try and mitigate that 2 to the n and run on real world code, we need to try and mitigate it anywhere we can and keep it to a minimum. So another interesting optimization is for struct initializations. So if we look here, we have our same structs, and then now we are defining them, or we are initializing struct y with 4 and 2 as a list value. Now, as you can see, how list values work in C code is they assign values in order of the field's appearance. So in other words, A always gets 4, B always gets 2, regardless of the configuration option. However, now, A5 and B6, which are associated with condition A, would always be the ones defined, as they're the first 2 values. So what we do is we manually assign values to each field associated with the presence condition that they are under. In A, we set to A5 and B6, and in not A, we assign to A7 and B8. Some other interesting optimizations that we had to tackle were flexible arrays, forward references, array initializations, and several other things that we unfortunately don't have time to discuss in this presentation. Some of the limitations of our code is that we do not evaluate expressions. So a negative sized array is a type error, but we don't announce it to be one. We also don't fully support variadic arguments, and we have chosen to not support K&R as we found they were outdated and unnecessary to support real-world code. Size of may also create some issues, as if we were to use the size of a struct in malloc, we would want the size of the struct that we've created to carve out the right space of memory, not what we would have used. So to evaluate SugarC, we check, does SugarC support more language features than existing desugarers? And can SugarC desugar real-world programs? And so, in order to check the first requirement, do we support more language features, we use Desugaring, our new micro benchmark that we've created, which is made up of 108 C files, all with configurations, and these are split into 12 language feature categories. The files were made small and without any bias towards any feature. The small files allow us to reason with them easily and check by hand for semantic equivalence. We have two metrics. We check for semantic equivalence, as in, does the desugared output match the equivalence of the input? And then specifically for SugarC, we check to see if we have execution equivalence, as in, do we output the same value as the original code would in the same condition? And so if we look at our results, we have three different colors. Green means that a feature for that tool was fully supported. Orange means it was partially supported, and red means it was not supported at all. And then in the end, we have the totals, which on the left side is the number of files correct, and the right side is the number of files that failed. And as you can see just by looking at the colors, SugarC supports far more language features than the other tools. Not only that, we can see that SugarC supports 97 of these 108 files, whereas C Reconfigurator and Hercules only support 32 and 73 respectively. So, in short, does SugarC support more language features than Hercules or C Reconfigurator? The answer is yes. You can also see that we've actually failed 2 files in categories that we've claimed to support, this being an FCI and semantic errors. And then, lastly, when we check SugarC for execution equivalence, we found that SugarC returned the same output value from the main function as the original code in the same presence condition in all but 2 cases, meaning 95 of the 108 files. So, can we run SugarC on real-world code? We ran SugarC on 3 tools commonly used for configuration research, being AXTLS, Toybox, and BusyBox, and this was due to their moderate number of files and large configuration spaces. In order to do this, we had to create a system configuration, which we try and remove macros associated with other machines and other operating systems that aren't our own, as we don't have access to all of their files and different libraries they could be calling upon. We've also turned off any macro assumed to be false, such as an inclusion guard, as all it does is introduce errors and doesn't explore any interesting configuration. Our metric is, can SugarC process this file and produce an executable output in 1 hour? And what we find is mostly yes. We support every file in AXTLS, every file in Toybox, and 516 of 565 files in BusyBox, with 39 failures. In BusyBox, for the files that we failed, 19 produced no result, as in it either timed out or it ran into an unsupported semantic action, or for the 20 that were produced but not compiled, these were due to things such as machine-specific assembly instructions that we didn't consider, as well as things like negative-sized arrays or invalid expressions. We also see that our files for Toybox and BusyBox ran on average around 50 seconds, and for AXTLS it was only 77 seconds, meaning it didn't take much longer. So yes, it can scale, and it runs on real-world code. So in conclusion, we've presented SugarC, which is a syntax-directed translation approach at desugaring for soundness. We also perform type checking and parsing simultaneously, which allows us to represent errors alongside real-world code and explore larger configuration spaces. We've also included some novel optimizations in order to actually run on real-world code. SugarC outperforms the previous work in terms of language feature support, and we have shown that it runs on real-world code. In the future, we are going to continue to update for features that we did not support, as well as we want to incorporate linking for full program desugaring. Lastly, we are going to attempt to make a framework in order to translate variability oblivious tools to run on our desugared output for variability aware analysis. Thank you for watching.